Hi guys, so I'm Utkarsh Gupta, and so I'm going to do this quick start round B 2021. It's going to start in about 1 minute and 30 seconds. And yeah, so as I said in an earlier video, that in this year 2021, I'll be trying to do all the Kickstart rounds and also cover all of them in a video. So yeah, it's just an attempt to continue that. And I already did Kickstart round A video. I'm pretty sure most of you have watched it already. So yeah, so today we'll be trying this, and I won't be wearing the mic because I like to be free during the contest. So yeah, so it will pretty much be off, and you can hear only the keyboard. So yeah, have fun watching. After that, we'll be doing the solutions as well. Hi, is my audio on? Okay. Yeah, so I ended this contest. I think like I did it pretty fast, not very slow. 1 hour, I guess, but too many silly mistakes. I got three penalties, so that will be 15 minutes extra for me. 15 or 14, I guess. 4 minutes. You see, like right now I'm ranked 18th, but I have too many penalties. So like for the next, uh, wait a second. I think for the next is it 13. Yeah, so for the next 7 minutes, I guess, yeah, for the next 7 or 8 minutes, people can keep surpassing me. So, yeah, I won't stay in the top 20 anymore, but I made it. Too many people on the front page have not done the B problem, I guess. Too many wrong answers on this one. Yeah. Even I had one penalty on all of these problems actually, and while this was like an actual mistake that I did, I actually forgot a certain case. These two were very silly. um, for example, like in this problem my penalty was just that I didn't have this line define int long long, which I usually use, but I had to remove that line while solving this C problem. So yeah, uh, this could have been this could have been a little slow. So that's why I removed the line define it long long from this code, but then I forgot to write it back again. And yeah, so that costed me, I think, 4 extra minutes of penalty. I think it's 4 minutes per submission. Yes. Yeah, 4 minutes. 4 minutes per penalty, right? So yeah, so it costed me 4 minutes there. I think am I in the rank maybe 2 or 3 again? Hmm. Yeah, okay. So I'm currently two, but somebody can surpass me. Probably Taran can surpass me. Uh, Wait a minute. Okay, I think Aryan can easily surpass me. Yeah, so if he does this quickly, he can also surpass me. But yeah, currently I'm 19th. If I refresh it, maybe it's 21 or something. Wait a second. Okay, it's still 19. Yeah, maybe I think the problem B was actually a bit difficult. Um, I won't say difficult, but like, yeah, it had some kind of corner cases or counter cases, something like that. So yeah, a lot of people didn't pay full attention to that, and that's why you can see a lot of wrong submissions on this second problem. On the other hand, if we talk about this problem, I think the constraints were like really high, and there might be a solution that might fit in those constraints properly. But my solution was kind of like a gamble. I mean, not really a gamble, but then yeah, like I wasn't too sure about it. I thought it could TLE, and uh, Nishant did just really nice. Um, yeah, so I can see. I think he made one penalty, but yeah, so he was like really quick, much faster than us. So Colin is also like he made less penalties, but ended up almost at the same time as us. But yeah, made much less penalties. We made three, he made one. Okay. Anyway, apart from that, let me see if my rank has gone down. Oh, it's ticking. So the thing is, just a second. Right, so I have 1 minute 30. Oh, sorry, 1 hour 30 minute 51 second total penalty, right? So after this is down to 1 hour 46 minutes, I guess. After that, nobody will be able to surpass me. But anyway, so congratulations to Neil. He won the round, and even he took 26 minutes. So yeah, this round I think was definitely tougher than usual. But the last problem was like really, really easy. I won't say easy, but it was like very standard. So yeah, so it was like a very standard problem, and I didn't have to think for like a lot of time. You can see that I ended up doing it in just what 15 minutes or something, right? So yeah, it was definitely like there wasn't much to think there. Like as soon as I read the statement, it was like pretty much obvious to me that okay, we have to do this thing. But yeah, obviously you need to be knowing about the things. There's this thing like this problem. We basically use a DFS and a segment tree. So you need to be knowing these two things, DFS and segment tree. And I think uh, like as the last problem of a Kickstart round, I think it was much easier than any of the previous rounds. And probably they could have swapped these last two problems. This felt more like a last problem to me than this one. Okay. 388 participants have solved, and 38 only 38 participants. Like this is actually much easier than any of the previous Kickstart rounds last problem that I have ever encountered. But anyway, so let's jump into it. Okay, yeah. So this is the increasing substring problem, the first problem of the contest. This was about. Let me connect my tablet by the way. I can explain using that. By the way, if I can hold this rank for like 3 minutes, I guess somewhere around 3 minutes. If I can hold it for like 3 minutes, then this would be my best Kickstart rank ever. My previous best is 23rd in round D 2020, right? So if I can hold it for like 3 more minutes, I guess, then this would be my new best. And this could have been my new best definitely if we hadn't done this stupid mistake here, which was just forgetting to put the defined int long long at any. Okay, so this was the first problem, increasing substring. Okay, so basically we call a string strictly increasing when all the characters are strictly greater than the previous character. Like for example, they have given us ABC is strictly increasing, ADF is strictly increasing, but ACC is not strictly increasing, and it is not strictly increasing because basically um, you can see C and C are equal to each other. So if you have any two characters that are adjacent to each other, and the character on the right is smaller than or equal to the character on the left, then you would say that no, these are not like this substring is not strictly increasing, right? So yeah, so something like that had to be done in this problem. I did a linear time solution, but wait a second. I think that was not required because yeah, okay, yeah. So basically, what I did was a linear time solution, but you could have also done it like you could have done something easier, right? So first, I will tell you the easier solution. The easier solution is something like it's actually pretty much brute force. There's just a cool thing that will guarantee that the solution will be fast enough. Okay, so it's something like, let's say you have a string. Let's take one from the sample itself, right? A B A C D A. Okay, right. So let's take the sample string A B A C D A. Okay, yeah. So what you can do is you can start from any character. Like we have to answer for each character the longest substring that ends at this character and is strictly increasing, right? So we can basically start from any character and we can iterate in the left direction and we can keep finding, we can keep checking if it is strictly increasing or not. And to do that, it is simple. Like we can start from here. We go here, we see that C is strictly smaller than D. So yeah, we will take CD into 1. Then we go one step more behind. So like that, we can keep moving to the left one by one step at a time. And then whenever we find a problem, like at this, we have a problem, then that's where we stop, right? So we get this string of length 3, which is the answer for this character. Okay, so like at this point the answer is 3. Okay, yeah, so that's what we have to do. You would think that this could be O of n square in the worst case, but no, this won't be O of n square. Right, so this would never be O of n square, and the reason it won't be O of n square is that there are only uppercase English characters in the string. Okay, so only 26 different characters. So the fact that there are only 26 different characters guarantees that for any character you will never move more than 26 steps, right? Because even if you have a Z here and everything is like strictly decreasing from that point, then also you will only go 26 steps. You cannot go more than that because like each character has to be strictly smaller than the next one. So that's why, uh, right? So that's why uh, you cannot have the length more than 26. So this solution will actually run in O of 26n, which is the same as O of n because we can remove the constants. So yeah, this is a linear time solution which would work for this problem. What I did was not this solution, I did something else. That would have worked even if the alphabet size was larger. Okay, so here we have basically only 26 different values, right? But if we had, instead of this string, if we had numbers and the numbers could range from 1 till 1 billion, right? Then also my solution would have worked in linear time. Okay, so I'm going to discuss my solution now. So my solution, what I did was I started from like this. Let me note down the example here. Okay, right. So I start from the left and I say that the mm, basically length the length at this point is 1, which is always correct because at the first position it is always 1. And when I move towards the right, I keep adding 1 if the next character is greater than the previous one. Okay, so this becomes 1 plus 1 equals 2. Then whenever I find um, two characters that are equal or the next character is smaller, right? Like basically when the strictly increasing property stops from holding true, then I again reset the count and set it back to 1. So like this, I can move from left to right and do it in linear time. Okay, so this is not even like this does not even depend on the size of the alphabet. So like even if we had a lot of distinct values, then also this would have worked in O of n time, right? Yeah, this was the solution that I submitted in the contest, right? So you can see, yeah, that's what I did here. I have a count variable. Okay, it is initially 1 and I initially print 1. Then I start my loop from the second character, and whenever I find uh, that the next character is greater than the previous one, I increase the count. Otherwise, I reset the count and set it to 1. And I'm just printing all the counts. And yeah, so that was the whole solution for this problem. Now we can move on to the next problem. But before that, I would like to see my final rank because now it cannot change. And it is again 23. So yeah, so I did not beat my previous record, but I stood up to it, I guess. Right. So yeah, so I have already made it to 23 and I did it again. Okay. Why has Adarsh made his email public? I'm sorry. Oh yeah. Okay. Okay. Yeah. I think he's probably like he's a batchmate of mine in my college. Anyway, so I can see a lot of people have now completed the contest. Uh, if I see the Indian rank list, I think I know a lot of people here. So Nishant, I know. Thundercracker, I don't know by the way. Who is this? Can I see the profile? Okay, I can't. Like, but I know Adarsh, I know Taran and Varnier. Obviously, I know Aryan and yeah. Okay, so hmm, okay, so these are the people who did the subtask. Okay, anyway, so yeah, that's pretty much. I think the rank list, rank list cannot change now because I have like for me, like my rank won't decrease now because even if somebody right now finishes all the problems, his time penalty will at least be 1 hour and 19 minutes, I guess. So this is definitely greater than this. So yeah, that's my final rank, 23rd. Okay. So yeah, this is the second problem. I also made a wrong submission here. It was pretty, I would say, careless of me to miss a few cases. Okay, but yeah. Okay, so this is the problem: longest progression. In this, basically, we want to find the longest subarray that is an arithmetic progression. Okay, so arithmetic progression we all know it is a sequence in which the common difference, like the difference between the elements, is equal, right? So we can see that in this we have the difference of 3 between all two consecutive numbers, right? So this is called an AP, an arithmetic progression, and yeah, that's what we want. We want a subarray that is an arithmetic progression, but we want the longest such subarray, and also we can change one element from the original array. We can change at most one element from the original array, right? So we have the liberty to maybe pick one element and set it to something else, right? So for example, it could have been something like, let's say, so we know that 1 2 3 4 5 6, this is definitely an arithmetic progression, but let's say the arithmetic progression breaks at some point, and here instead of 6 we have, let's say, 100, right? So what can happen is after that we can again have 7, 6, 7, 8, 9, 10, 11, and so on, right? So what we can do is we can replace one of the elements and put, okay, I'm sorry. Okay. What we can do is we can replace one of the elements and put the missing element here, so that these two intervals kind of get combined with each other, and then they form a singular long AP. And yeah, we can take the length of this AP, and this could make our answer, right? So basically, this was the central idea to my solution. Initially, I only thought of this case. There are some corner cases, like when the element that we change is at the end of the array or at the starting of the array or something like that. Yeah, there are definitely some counter cases there. But the initial idea of my solution, how I thought of it, was basically something like this only. So I had an example like this in my mind, that we have a block of arithmetic progression subarray on the left, and then we have a similar block on the right, and one of the element is not agreeing with the two blocks. So what we do is we remove this element and we put the element that should actually be here, and yeah, so that's how this block gets completed, and we basically add the answer from both of the blocks. Okay, yeah, so I tried to implement this solution, although there are a lot of corner cases there. I will be discussing those in a few minutes. But let's say if this is the most general case, I guess. So if we have to cover this most general case, what is the information that we need? Okay. So basically, I will try to change each element one by one. And the thing is, whenever I change an element, I will always put it as the arithmetic mean of these two elements, right? So like this is 5 and this is 7. So I will always put the element 5 plus 7 by 2, that is equal to 6. and I'll do this because I want this difference and this difference to be same. Okay, so what I can do is I can go to each of the elements, each element in the array one by one, and basically I can replace that element with the arithmetic mean of the two adjacent element to itself. Like instead of this 5, I can take this 4 and this 1000 and try to put 502 here, right? And then I can try to combine the intervals from both the sides, right? So obviously I can do that. I can try doing something like that. So to do this, what kind of information I want? So since I'm trying to replace each element, so I want to know for each element, if I replace this element, what is the size of the block on the left and what is the size of the block on the right. Okay, so I want the size of the blocks on both directions, right? So basically this 5 should contain a 5 here, which means that we have an arithmetic progression of length 5 on the left, right? And then this 7 should also contain a 5 here. This means that there's a arithmetic progression of length 5 on the right. So basically what we're storing here is this will store 5, this will store 4, 3, 2 and 1. Okay. Similarly, this will store 5, 4, 3, 2 and again 2. Okay. So why is this 2? This is 2 because these two elements are kind of forming an arithmetic progression, right? So like two elements are always in arithmetic progression because according to definition, you want all the differences to be same, and since there is only one difference here, it always agrees. Okay. So here also we will have 2, here also we will have 2 because as I said, these two elements will always agree, right? So yeah. Then at this point again we have 2 because these two will agree. Here again we have 2 because only these two are agreeing, then 3, 4 and 5, and here we have 5, 4, 3, 2 and 1. Okay, something like that. So the numbers that are written on the top mean that if you take these many elements on the right, these are forming an arithmetic progression, and the number that are written on the bottom mean that if you take these many elements on the left, these are forming an arithmetic progression, right? So yeah, so that's what I'm storing here, and now it's kind of easy to try to remove an element. So basically if I try to remove this 1000, I know that I will put the arithmetic mean of 7 and 5 here, so I will put 6 here, and then I will add this 5 and this 5 to the answer. So basically my answer will be 5 plus 5 plus 1, basically this element and this and this. Yeah, so basically that's what I did in my first submission, and it got wrong answer because I was very careless here. There are a lot of mistakes here, and I didn't consider any of those. So yeah, that's the reason why I got the wrong answer. So now let's talk about the additional things that we need to take care about, right? So first of all, um, right, so like if this is a 5 and this is a 7, we know that if we add these two and divide them by 2, we will get an integer. But then if one was even and one was odd, like let's say if it was 5 and it was 8, so if you take the average of 5 and 8, it is 6.5, and yeah, so that is not allowed. So basically we are allowed to replace a certain element only if the two adjacent elements add up to give an even number, right? So even after that, let's say if you put a 6 here, so we know that this distance and this distance will be equal, that is equal to 1, right? So we also need to make sure that the arithmetic progression that we have on this side actually has the common difference of 1 as well, right? So this is something that we need to take care about. uh, you can see a counter example here. So let's say if we had the array like 1 2 3 4, and then let's say again we have 1000, and here we have 8, 9, 10, 11 and so on, right? So what will happen is you will try to remove this element, put the average of these two elements here, that is 6. Okay, but the problem here is this distance is 2 and this distance is also 2. while the common difference in this AP is just 1, and in this AP also it is 1, right? So obviously we cannot combine these two things. So basically we want this difference to be equal to this difference, the difference between these two elements, because we already know that these two differences and these two differences will automatically be same, because these are forming an arithmetic progression. But yeah, we want this difference to be equal to this difference, and this difference also to be equal to this difference, right? But if those things are not following, right, so if those things don't take place, then what can we do? So let's try to figure that out. um, let's see what we can do if those distances are not following. Okay, so one thing that could have been possible is that it could have been following on one side, right? So let's say if I erase this 1 and 3, right? So if let's say the array was just 2, 4,000 and so on, right? So you can see that this 2 is not complying with this difference of 1 on the right side, but it is complying with the difference of 2 on the left side, right? You can even have something like 0, 2, 4 and so on, right? So all of these elements can be combined with this and also with this, right? So you can have an interval like this from this 8 till this 0. As you can see, the differences are 2 everywhere, right? 2, 2. So if the common difference of on one of the sides is equal to the difference between the elements that we replaced and the adjacent elements, then it's fine. We can take the left window plus 2, or if it is matching with the right window, we can take the right window plus 2. Okay, but in general, even if it is not matching, then also we have a lot of things that we can do, right? So let's say even if we had something like 1, 2, 3, 4,000 and then um, 11, 12, 13, 14, etc., right? So even if we cannot get an integer by taking the average of these two elements, then also at least the least we can do is, instead of this 1,000, we can put a 5 here, right? So this will increase the size of this window by 1, or we can also put a 10 here, that would increase the size of this window by 1. Okay, so we can either extend the right window, we can extend the left window, or we can put the average of the two elements here if the sum is even, and then we can take the common difference between these two elements, and then if it is agreeing with the left side, then we can extend the left side and add 2 to it, and if it is agreeing with the right side, then we can extend the right side and add 2 to it, and if it is agreeing with both the sides, then we can add both of them and add 1 to it, right? So yeah, so a lot of corner cases here, not exactly corner cases, but a lot of casework here that you had to do. And yeah, so that's all I had done in this problem. Okay, so first of all, I had two arrays in this problem, count and count r. So basically this is count and count reverse basically. So the array on the bottom is count for your reference, and the array on the top is count reverse. Basically I just um, counted all this. This is just some naive techniques. This technique is actually kind of similar to the technique that I used in the first problem. Like whenever the common difference is same, I increase the count by 1, and whenever it is not same, I reset the count to 2 again. Okay, right. So once I calculate these two arrays, after that I will try to replace each element one by one, except for the first and the last element, right? So I know that there is nothing on the left side of the first element and on the right side of the last element, right? So what I can do is I can always convert the first element into an element that would agree with the block on the right, and then I can always change the last element into an element that would agree with the block on the left, right? So initially I assigned answer to the maximum of 1 plus the block that starts at index 1, comma 1 plus the block that ends at index n minus 2. So basically at the second and the second last index, the blocks that are present, I extend both of them by 1, and that is my initial answer. And then I will try to replace each element except the first and the last element. So you can see in this loop I have strategically removed the first and the last element from this loop, because a lot of the things in this loop won't even be defined for uh, a lot of the things that are going on in this loop won't be defined for 0 and n minus 1 basically. Okay, so Yeah. So these are the two things that I initially said, that we can extend the block on the left or we can extend the block on the right by one. So obviously this is what's happening there. Then if the sum of the two adjacent elements is odd, then obviously we cannot do anything and we continue from here. But if it is even, then I take the common difference between the two elements, basically the total difference between these two elements and the half of it. Okay, so when I have the half of that thing, I will I will find whether this difference is equal to the difference in the blocks on the left and the right. Okay, so yeah, basically, wait a second. Right, so this means that this difference is equal to the difference in the block on the left side. So I add 2 to the answer to the block on the left side, and this means that the block on the right side has the difference that is um, equal to the difference, current difference, basically the difference that we created by replacing one element. So I'm adding 2 to that as well. And finally, this means that uh, the difference at this point is not equal to the difference in both of the blocks. So then I'm continuing. Otherwise, this is the base case, the initial case from which we started thinking about the problem. We take the right side block, we take the left side block, we add both of them, and then we add one extra to that, and that becomes our answer. And yeah, so that then we print the answer. Okay, so maximum of all these cases, that's what we're printing here. Right, so a lot of casework was involved here. I even got a wrong answer because I forgot a lot of these cases. I think I forgot this entire part. So yeah, that's why I got a wrong answer. I believe a lot of other people also got wrong answers in this problem, because you can see that there's a lot of red here. 1700 people failed even the test set one, right? And not a lot of people passed any of the sets, right? Okay. Anyway, so now we have this next problem, that is consecutive primes. Okay, so I don't have the exact proven solution for this, but I just kind of used some of my common sense and searched a few things here and there, and it kind of worked out. So it got accepted finally. The wrong answer was basically a silly mistake. So, like, there was a simple corner case that I forgot to include. So yeah, that was kind of like a silly mistake. I should have not hurried and checked it on that. But anyway, yeah. So basically, the problem is like, this is a long statement. Let's forget that. So basically, the problem is you are given an integer z, and what you want to do is you want to find a number that is smaller or equal to z, and is the product of two consecutive prime numbers. Okay, what we mean by consecutive prime numbers is that, like, let's say you have these prime numbers 2, 3, 5, 7, 11, 13, 17, etc. Right? So if you multiply any two consecutive numbers, like let's say if you multiply 7 and 5, you get 35. If you multiply these two, you get 77. Right? So you will get a lot of these elements, and what you want is you want the maximum element that is smaller or equal to the given z. Okay. So what one would think in this case is, like, at least for the small constants, yeah, at least till 10 to power 9, at least till the test set 2, what you can do is you can the you can make a sieve of all the prime factors, all the prime numbers till square root z. Okay, so basically you can have square root z, and you can basically store all of the prime numbers that are smaller or equal to square root z, maybe even a little larger than square root z, but not a lot larger, right? So I would say if you store all prime factors till, I think, 5 into 10 to power 4, that would be enough. That would be more than enough, I guess, right? So if you store all of these prime factors, what you can do is you can store the product of all two consecutive numbers in a vector. Like you can store 6, 2 times 3 is 6, then 3 times 5 is 15, 5 times 7 is 35, and then 7 times 11 is 77, and so on. So you can store a long vector of about 50,000 elements. And then what you can do is whenever you have the query for a z, you can just binary search this vector, and you can get your answer. Even I think even a linear search would work. It probably shouldn't fail because there are not a lot of prime numbers till this range. I think there are around 5,000 prime numbers or even less than that. In general, the number of prime numbers till n are n by ln n, right? So anyway, approximately. Okay, so yeah, so that would be enough to pass the test set 2. But with test set 3, I don't think this type of solution would work. I mean, it could work, but I won't place my bet on it. If you try to sieve up till 10 to the power 9, it will be like really slow, especially if you're trying to store all of the prime factors. So what I did was, I like the central idea of my solution is to basically start with square root z, try to find a prime number that is just smaller than this, then try to find a prime number that is immediately smaller than that, and find a prime number that is bigger than this, right? So definitely our answer will either be PQ or PR. Okay, so the answer will be P into Q or it will be P into R. Okay, there is no other option here. It will definitely be P into Q or P into R. Okay, and yeah, so we can easily find square root of z. That's not a problem. But how will we find P, Q, and R? How to find the nearest prime number to a certain number? Okay, for that I utilize the fact that prime numbers don't have very large gaps between them. Okay, so it's called prime gap. So I actually opened the Wikipedia page of prime gap during the contest, and we are given a frequency distribution graph here. So I kind of looked at it and saw that, yeah, so the largest gap between two prime numbers is not more than 9 into 10 to the power 6, right? So the largest gap between two prime numbers is not more than 9 into 10 to the power 6, and even that is not a very likely case. So I thought, like, if we are given a certain z, then in just 1.8 into 10 to the power 7 operations we can find one prime number on like both of the sides. Maybe one point, like not more than 10 to the power 7 operations, right? And I know we do have 100 test cases, so it goes beyond 10 to the power 9, but then we also have 15 seconds, so it can work, right? So that was my main idea, that it can probably work, and I tried to do it just based on this prime gap graph that I have. And yeah, so it kind of worked, and I'm glad it worked because, yeah, so that was the central idea behind my solution. But still I need one more thing right now, and the thing that I need is, um, I need to be quickly able to find two prime numbers. I'm sorry, I need to be quickly able to find whether a given number is prime or not. So what I need to do is called a primality check. Okay, so I need to do a primality check quickly. Okay, so one of the fastest primality check is actually the Miller-Rabin test for the given constraints. The Miller-Rabin test is actually one of the fastest primality check, but we couldn't use it here because even that is, I think, around log of n. Like basically it is log square n, but for a given bound you can smartly make it log of n. Okay, so even with this log of n, um, even with this log of n test, I think it is really slow because, like, 9 into 10 to the power 6 I already have, and if we multiply, let's say, 20 to it, then it is like very slow. So yeah, that's why I didn't want to use any primality check. So what I did is I basically used sieve of Eratosthenes only. So I used sieve of Eratosthenes, and you'd think that uh, I'm back to square one. Like when I started the explanation of this problem, I said that we cannot use sieve of Eratosthenes because the array is too long. But I didn't use any normal sieve of Eratosthenes. I use a special, very highly optimized code that is called the Yarin Sieve. So basically, Yarin is a coder, a competitive programmer actually, and he wrote a very optimized code that is called Yarin Sieve. You can Google it and find it easily. Okay, Yarin Sieve. Right. So yeah, so this is basically the Yarin Sieve. You can use this. It is like very very fast. I know that for 10 to power 8 it works in like 0.7 second or something like that. So I knew that for 10 to power 9 also it won't take more than 7 seconds, which is kind of fine, I guess. Like even if it does take 7 seconds, that's fine because we have 17. Sorry, we have this is the wrong problem. Yeah. We have 15 seconds per test set, and we are running the Yarin sieve only once per test set. So I knew that this would probably work, and yeah, so basically that's what I did in this problem. Hmm. They don't show us the runtime of the problem, like they don't show how long it took to run on their computer. But anyway, so okay, so I just a second. Right, so I copied the code for Yarin Sieve. Then I ran Yarin Sieve once so that I can quickly find whether a number is prime or not. So basically, it uses this expression to find whether a given number is prime or not, and it actually works in just I think O of one time. That is kind of nice. So yeah, so it works in constant time. So once you pre-process it in I think around linear time, or like the time it takes to run is almost linear. Like it is very very optimized. So the pre-processing is almost linear, I guess, and after that maybe linear or like something like n log n or something like that, but very very optimized. Okay, and then this is prime function works in just O of one time. So what I did is I took the z as input, and this is the counter. This is the corner case that I earlier missed. So my code was giving unexpected output for z smaller than 15, and I can explain that, but I won't. You can it is left as an exercise to the viewer itself. Okay, so I find the square root of z. After that I find the smallest odd number that is smaller or equal to greatest odd number that is smaller or equal to z, sorry, the square root of z. And after that I find the greatest prime number that is smaller than that. Then basically these are PQR. So as described here, these are the PQR that I find. So first I start with the square root of z, then I find the nearest prime number that becomes the square root p. Sorry, that becomes p, and a number that is even smaller than that becomes q, and a number that is bigger than that becomes r. So then I compare whether pr is smaller or equal to z. If that's true, then I print that. Otherwise, I print pq. Okay, right. So, and for this problem, I removed define int long long from the top of the problem because I already know that this code is not very fast, and even these parts are also not very fast. So what I wanted to do is I want to make sure that my code is running fast. So I removed define int long long, and that is exactly what caused this wrong answer in this problem. So I never added define int long long in this problem, and that fails because even the input is greater than um, uh, 10 to power 9, which overflows the integer range. Okay, so yeah, so I quickly fixed it. I think within 1 minute or something I realized that this is the part that I'm missing, and I fixed it and resubmitted. Okay, Yeah, this problem was kind of, um, I would say it was kind of very, very simple actually, like very standard in fact, right? So the main thing that you have to notice in this problem is that all Li are distinct, and this is one thing that is not given in this initial problem statement. And if you don't pay attention to this part, you can still solve it, but then the solution is much like much tougher, I guess. Maybe not much tougher, just a little tougher. But yeah, so it will be tougher if you don't notice this part. Okay, I just realized it won't be very tough, but yeah, it will definitely be tougher if you don't realize this part. Okay. Anyway, so basically what we have is we are given a tree, and each day what you do is you pick up a certain node of the tree, and then you take a path from that node to the root. The root is the one. The root is the node one or the city one. So you take this simple path that is connecting the taken city to the node one, and on that path you will travel with the load of weight W, and you will pay for each road. You will pay a toll of amount AI if the weight is greater or equal to the limit of the road. Okay, so each road has a limit, and if you have to just a second. Right, so each road has a certain limit, and if you have um, the if the weight that you're carrying is actually greater than the load limit of the road, then you have to pay a certain charge amount. Okay, so in general, the total charge would be the sum of all the weights, but that's not what they're asking in this problem. So they're asking, instead of the sum of the weights, they're asking you to print the greatest common divisor of all the toll charges. Okay, so this was mainly just a desperate attempt to make the problem a little less standard, but it is still very standard. Okay, so uh, uh, let's see how we can easily simplify it. But before that, first let's try to understand the problem. Okay, the problem is kind of simple. You have a tree like this. Okay, and in this tree, basically, you can like each node has a limit, and each road, basically each road has a limit and a cost. Okay, so limit and cost, each of the road has these two parameters, and each of the query is given by two parameters, that you are given a node. Okay, so query is given like you are given a city and a certain weight. Okay, so the city could be one of the cities of the tree, and the weight is just a parameter of the query. Okay, so you will consider all of these edges that connect this city to the node 1. You consider all of these edges, and among these edges you will take only the edges which have the let me write Li and Ai here. Okay, so you will only consider the edges such that Li is smaller or equal to the W. Okay, yeah, so that's what you want. So among these edges, you want the edges with the Li smaller or equal to W, right? And then what you want to do is, for each such I, so I such that this thing is happening, you want the GCD of AI. Okay, so you want the GCD of all such AI which um, which obey this thing, that Li is smaller or equal to W. Also, only the ancestor edges are considered. Okay, so that's what we want to do. If we wanted to perform online queries here, then it could have been a little tough, but we don't have to do online queries here. We just have to do offline queries. And what I mean by offline queries is that you have all of the queries at once. You can sort them in a certain way, and then you can solve them one by one in a suitable order of evaluation, right? So you can incrementally increase your answer and then answer queries like this. So since the queries are offline, what we can do is we can actually perform a DFS on this tree. Okay. Yeah. So what we can do is we can actually perform a DFS on the tree. Okay, let's say we perform a DFS like this. First we go till here, then we go back up, then down, then up, then down, and so on. So let's say whenever we reach a vertex, we have this entire path in the stack. Okay, so we know that DFS has a stack. Even if you use recursion in the background, somewhere it has a stack. Okay, so we know that all of these edges are currently like we are currently down these edges, right? So these are present in the DFS stack. Okay, so we only want to consider the edges that are present in the stack, and out of those edges we want the uh, edges that have again li smaller or equal to w, right? And we want GCD of all those things. Okay, so yeah, so the idea is pretty much very standard. I think most of you must have understood it by now. So basically we just have a segment tree. Okay, so in this segment tree what we will do is at the index li we will put w there, sorry, and at the index li we will put ai there, right? So if this index is li we will put ai there, and then to solve a query we will find the index w, and we will take the GCD of all the elements from 0 till w. Okay, so for that maybe you need to know how to write GCD, a segment tree that supports GCD queries. So for that you can actually go to my course that I have done on segment tree earlier. I have done a course on segment tree. You can check it out if you're interested. Sorry, somewhere here, right? So yeah, so I've done a course on segment tree, three different lectures. You can check those out if you're interested. I'll put the link in the description. I'll put the link of all these classes in the description of this video. If you're interested, you can check it out. But yeah, so basically that's what we're doing here. And since the allies are distinct, when we go out of this stack, we can just remove this ai and put 0 here. Okay, if allies were not distinct, then we had to do something like let's say the element that was present here was capital X, then we would have to store this X somewhere and then replace this with the GCD of X comma AI, and then perform the other queries, and after that again replace this GCD of X comma AI with X, right? So this is something that we would have to do if li wasn't distinct, but since li is distinct we can just put ai here, and when we go out of a certain node we can put 0 again, right? So yeah, basically that's what the problem was. Make the tree, store the queries at each node, perform a DFS, and maintain a segment tree, and that's it. Just answer all the queries. Yeah, so for this I used my generic segment tree template, which I can easily convert into any type of segment tree. You can see just by writing I think 6 lines of code I was able to uh, create the entire segment tree, because I have this template pre-written, okay, which you can understand by going to my course that I'll put the link in the description. Okay, anyway, so yeah, after that it is pretty much simple. Just the answer for any query is just the query the segment tree for weight 0 till w, and to go down the DFS, like to go down the tree, we're basically just putting a on the index L, and when we come out we put 0 there again. Yeah, so basically that's what we're doing, and that's it. So it was like, if you don't know segment tree, obviously you'll think that it is difficult, but it was like very standard and much easier than any of the last problem of a Kickstart round that I've seen till now. Okay, and yeah, mm, that concludes the editorial for this. And why is my rank 62? Okay, yeah, this isn't refreshed. Okay, yeah, so I ended up getting 23rd rank on this. um yeah, so definitely not better than my best performance, but yeah, equal to my previous best performance. In the in the immediately previous, like definitely the best performance of mine in 2021, because in round A I had 29th rank, although the Indian rank was 2, which is still 2 again. So yeah, anyway, so I think this was although in the previous round I think I personally did better. Today I made a lot of silly mistakes, and if I hadn't done these, like obviously I couldn't have avoided this one. It was a deep mistake, but these two could have been avoided easily, and then I would have around 8 minutes less penalty. And with the 8 minutes less penalty, let's see where would we would have been. So with the 8 minutes less penalty, let's subtract 8 from this. So that is, I think, 1 hour 5 minutes and 51 seconds here. So we would have been 16th then, uh, if we hadn't made these silly mistakes. But yeah, that's just an apologistic argument. Uh, you gotta own up to your mistake. But yeah, also try to be like, one has to try to be careful in the future to not repeat the mistakes. Yeah, in this contest, I think most of the mistakes happened because I was in a hurry. I was maybe trying to finish the contest too quickly, so I was not double checking everything. I think I should work on it and not do that next time. So yeah, so that concludes this video, and thank you for watching.